Okay, let's talk about another prototype for kind of prototype model for linear programming, which are what I think of as flow models, and that they involve the flow of something from node to node. And the basic idea behind these is that you can often draw a diagram with some kind of a flow chart diagram where you've got some quantity moving from node to node, and you're generally governed by some sort of equation that, or your constraints end up being that your inflow has to be equal to your outflow, or yeah, usually something along those lines. And so take a moment, pause, read through the scenario so that you understand it when I start discussing it. But yeah, take a moment, read it through, pause the video. Okay, now that you've read through the problem, I'll sort of summarize it as I start solving it and drawing a picture for it. So the key trick with these flow models is draw a picture. If you can draw a picture, you can usually come up with the flow model not too bad. So city has funding requirements for a capital project of 2 million, 4 million, 8 million, and 5 million over 4 consecutive years. They need to raise that money by selling bonds, and those bonds have different interest rates, and we've got a forecast for what those interest rates are going to be over the next several years. This is a simplified problem. Doesn't perfectly match up with how kind of bond scenarios for capital projects actually work. So you'd have to modify this to actually make this work in reality. But we're going to make a simplifying assumption that the bond interest payments all start 1 year after the project is complete and continue for 20 years. At which point the bonds, then you pay back the whole amount of the bond. And so our goal here that we're going to do is we want to essentially minimize the cost, the yearly bond payment over the life of those bonds. So in what way can we sort of plan out when to borrow to try to minimize our bond payments, or minimize the interest paid on those bonds? Okay, so let's think about diagramming this as an inflow and outflow problem, or a flow chart. And so essentially we've got each of the years are going to be the nodes in our flow chart. And so if we think about year one, and in this case, the flow, the item that's flowing is money. So money flows into the bank accounts of the city, and it flows out of the bank accounts of the city. Essentially we can bring money in by selling bonds. And so I'll call this, actually we'll give this a name, B1. That's going to be one of our decision variables, and that I can sell B1 amount of bonds in year one. Okay, and so each of these little arrows comes from selling bonds. Okay, what flows out in year one is essentially project expenses. And in year one, the project expenses end up being 2 million. Okay, we're going to kind of denote our units for this problem as millions of dollars, and so that we don't have to write out as many zeros. Just means that when you get your final answer, and the final answer is an optimal objective value of 2, then you got to kind of say, interpret that as 2 millions. Okay, and so we can sell bonds, and we can do project expenses, and if that's everything, then we sort of sell exactly 2 million bonds in the first year to cover those expenses. But the tricky part is that we can sell more bonds than we need. So we can sell more than 2 million in bonds and have the resulting money flow through to the next year. And not only does it flow through as is, but it actually gains a little bit of short-term interest. Okay, so notice the short-term interest is not nearly as good as the interest that we'll have to pay on the bonds in the long run, but Essentially that short-term interest makes it so that we can kind of flow our money through and gain a little bit if we borrow at the right time. Okay. So that will then flow into year two. In year two, we'll sell more bonds. How many bonds? Well, we'll denote that as a decision variable. So anytime you're like, well, how much? Make it a decision variable. And the outflow from year two is 4. And then whatever is not used will flow on to year 3. We'll sell B3 bonds in year 3, and the capital requirements, that's where the project looks like it reaches its peak. We got to sell 8 million there, or we need to have 8 million to cover the project expenses. And our last year, we'll sell a certain number of bonds, and the capital requirements will be 5 million. Okay. And so whatever essentially doesn't get used flows on. And actually, as specified, we could solve the problem with just these flow variables. But for bookkeeping and readability and sort of ease of understanding, as well as gaining some additional information, it helps to add some extra variables that account for how much flow is in each of these years. So let's actually label these, and I'm going to call them F1 for the flow from year 1 to year 2. And note that because we're getting interest, it flows out of year 1 as F1, but it flows into year 2 with interest. So it'll be 6% interest. So we'll do 1.06 times F1 is the amount flowing into year 2, where all of F1 flows in plus 6% more gives us 1.06 F1. Flowing into year 2. We'll do the same for the flow coming out of year 2, and it's going to pick up some interest of 5.5%, so 1.055. F2 flows into year 3. F3 flows out, and it picks up 4.5% interest as it flows into year 4. Okay. So that is the essential idea of a flow model is can you diagram sort of what's kind of moving through the model, what's the inflows, what are the outflows. So let's denote now our decision variables. We sort of labeled on them on here is that BI is the amount of bonds sold in year I, for I equals 1, 2, 3, or 4. Okay, and amount of bonds in millions of dollars. Okay. The other flow variables are going to be these F flow variables. They're going to be amount of money flowing from year 1 to 2, 2 to 3, and 3 to 4. Okay, and so this is for I equals 1, 2, 3. We're gonna have 3 of those. Okay, it doesn't quite, kind of a little bit weird because the flow is in between the years, and so whether we talk about it as the year it's coming out of or the year it's going into, it doesn't matter too much. Okay, so those are our decision variables. What's going to be our objective? And if you knew a little bit more about finance than I do, you might become able to come up with a better objective than just this, but we're going to assume that we're paying the interest on the bonds, simple interest. And so we want to minimize our interest payment that we're going to have to pay over each of the 20 years. And so minimize interest payment. on the bonds. And that interest payment is going to be tied to the interest rates in each of those years. And so it's going to be 0.07B1 plus 0.06B2 plus 0.065B3 plus 0.075B4. Okay, and those come from the various interest rates that we've sort of projected going into the future, that we expect interest rates to be changing over time. And so I'm skeptical that they're able to forecast those interest rates so well into 4 years out into the future, but I guess they've got some idea that they think it's going to go down and then come back up. So they must hire some pretty good econometrics people. Okay, now let's talk about constraints. The main constraints are going to be of the form inflow equals outflow or outgo. And so the sum of all the ins to a node has to be equal to the sum of all the outs. And so we'll have one of these constraints for each node. And so let's look at node 1. What goes in? Well, B1 is the money flowing in. Flowing out is $2 million as well as F1. And so the in is B1 has to be equal to the out, which is 2 plus F1. Okay, and most of the time, most solvers, the way we set it up is that we have to get all our variables onto one side, usually the left side, and all our numbers on the right side. And so we'll rewrite this as B1 minus F1 equals 2. Okay. Now we can do the similar thing for node 2. Node 2, notice we got 2 inflows now. We got both our flow variable from year 1 coming in as well as our bonds that we sell. And so if we had enough flow, we wouldn't have to sell any bonds in year 2. And so 1.06 F1 plus B2 equals our outflow, which is $4 million to cover the bonds, plus the flow out of year 2 and into year 3. And if we rearrange this to get all our variables onto the same side, 1.06 F1 plus B2 minus F2 equals 4. Let's repeat for node 3 and node 4. The in is going to be 1.055 F2 plus the bonds that we sell in year 3. And that has to be equal to our outflow of $8 million plus the flow from year 3 to 4. And then we'll do the same thing for node 4. We've got an inflow of 1.045 F3 plus the bonds that we sell in year 4. And that has to be equal to the capital outlay in year 4. And notice that there's no flow now at the end of year 4. We're not going to carry over any money into other capital projects. And so these are the other 2 constraints. And we can again rewrite them so that they'd be ready to enter into a linear program as 1.055 F2 plus B3 minus F3 equals 8, and 1.045 F3 plus B4 equals 5. Okay, and so here's our 4 constraints. In addition to those constraints, we'd have positivity constraints or non-negativity constraints. We wouldn't have to worry about integer constraints for this problem. One thing I'll point out that's maybe a little bit different than previous problems is that all these constraints are equality constraints. In the previous examples, we only had less than or equal to or greater than or equal to constraints, but we can also have equality constraints. kind of makes you think that our feasible region is now actually in a sort of 7-dimensional space, because we've got 7 total decision variables, but it's a very flat 7-dimensional space because of all these equality constraints. And so, yeah, if you've taken maybe a little bit of Calc 3, you may be able to think about maybe how you could eliminate these constraints to actually eliminate variables. And you could do that. You could eliminate essentially 4 variables using these constraints and then get it down to just 3 variables with just the positivity constraints. But we're not going to do that. And I generally advise against it, in that the linear programming computer programs will do that for us. And that usually I recommend adding as many variables as makes your problem easily readable. And so adding the flow variables here, while they weren't 100% necessary, they definitely make the problem much more readable. Okay, if you didn't add flow 1 variable, well, we can really look at this equation here and know that, well, flow 1 is B1 minus 2. And so you could have used that as the flow into year 2, as B1 minus 2 is flowing in. But it would have really quickly gotten pretty ugly because you would have taken that times 1.06 and sort of you would, yeah, it just gets really ugly really fast. And so introduce flow variables. They're not really a decision that you make, because all the money that you have extra after a year flows into the next year. But they're sort of what I think of as bookkeeping variables. And they give you actually some extra information about the problem of how much money do you have in your account from year to year throughout the project, which not a decision you need to make, but it's maybe important information that you'd like to know if you are managing this project. So this is a prototype of a flow model. Flow models show up a lot of places. It's not always money that's flowing, but maybe work orders or something like that, where if you don't complete the work in one day, it moves on to the next, but maybe you have some deadline at the end of the week that all the work needs to be done by that point in time. And so you can think of maybe work orders flowing through a flow model, and you allocating resources throughout the week to satisfy those work orders.